review of what. All right. So it's going to be so this is going to be a very brief review of what 11D supergravity is. So the component perspective, and then I'll also tell you the 11D n equals 1 superspace formulation of 11-dimensional supergravity, and in both of these perspectives, how the equations of motion are forced on the theory will be described. And then I'll give you a proposal for a solution of this, or a partial solution of the problem, whereby we managed to throw 4 of the 32 supersymmetries off shelf by adopting what is called 11D n equals 1/8 superspace. So there is again going to be a mix of 2 different approaches which we are going to take. One is a bottom-up approach, which is more or less finished, and this is based on a series of papers really that came out of the Becker group, and I'm going to focus on 2 particular papers in that series, and I'm going to tell you how to embed 11-dimensional supergravity component fields in 4D n equals 1 superspace fields. So this bottom-up approach is pretty finished and published already. So it's 3 potentials of 4D n equals 1 superspace, which will house all the component fields of 11D supergravity. And the main driving principle in this approach is the symmetry considerations, the manifest and non-manifest symmetries that we have. And then in the top-down approach, here we are going to take a look under the hood. So this bottom-up approach has many 4D n equals 1 superspaces, and I already mentioned that we are talking about an 11D n equals 1/8 superspace. So in this top-down approach, we are going to explore what the supergeometry of that superspace is like, and how the different constructions that we have here, constructions of the frame, the gravitino, and the 3-form superfields, and so on, they will have different kinds of differential identities between themselves. So from the perspective of the bottom-up approach, it might not be evident how many of these differential identities we have and why. So this top-down approach will tell you that it is essentially the supergeometrical Bianchi identities that will force all those differential identities on top of this construction that we have here. So this is a work in progress right now with Catherine, Artem Bolshov, Nathan Brady, Daniel Butter, and the other previous work was also done with Melanie and William. So this is going to be the brief plan. And in the end, I'll end with a sort of motivation of why this problem is important or interesting other than mathematical curiosity. So what do we want to achieve by constructing the supergeometry in this fashion? So that's the brief plan of the talk. And let's now take up the first part, which is a statement of the problem. So I don't want to be erasing this part, and I don't want to stray off the board because this part and that part is out of the view of the camera. So let me just erase this again.
Any reason why motivation is left unconventionally to the left?
Well, from this, so I thought of that, but right now from the starting point, my motivation is just a mathematical curiosity. And later on, I'll tell you what else we can do with the results of the project. Okay. All right. So, good. All right. So let me first tell you why 11-dimensional supergravity is on shelf. So this is from 1978. Cremmer, Julia, Scherk, they wrote down the 11D supergravity theory, and the content, the field content is very simple. We have a frame field, a spin 3 half gravitino, and a 3 form in 11 dimensions. Right? And they wrote down an action. So before I go into writing down the symmetries and the action, let me do a simple count of how many degrees of freedom these fields have. So on shell and off shell, these quantities have these many degrees of freedom. You can do a simple count. This is 44 and 55. This has 128 on shell and 320 off. And this one has 84 on shell and 120 off shell. So if you do a count of how many total bosonic and fermionic degrees of freedom we have, on shell they match, but off shell they do not. So this is 175 bosonic plus 320 fermionic. Right? So actually, the original argument that Cremmer, Julia, and Scherk use in proposing this model is a simple. So they start with this simple field content because they first count the on-shell degrees of freedom in the frame field and the gravitino, and they say that there is a mismatch, and it happens to be the same number of degrees of freedom that a 3 form in 11 dimension will have on shell. So they propose that that would be the other element in the content. So that way they manage to have an equal number of bosonic and fermionic degrees of freedom, but clearly you see that off shell they don't match. And that's how on shell versus off shell goes. If you have an on shell theory, usually off shell degrees of freedom don't match, and you need to introduce some new auxiliary fields to make the counts match, and then you write down modified supersymmetry transformations that would close off shell. So in the bottom-up approach by construction, I'll give you a field content where this problem has been fixed, and we eventually end up with an equal number of bosonic and fermionic degrees of freedom by introducing some auxiliary fields, and there would be some compensating fields as well, and I'll mention those. Right? Good. So what are the symmetries of this theory? So there is an action, of course. The action is I'll write down some crucial terms in the action. Let's not worry about coefficients for the moment. I'll write the easier ones, and I'll skip the more difficult to remember fractions. So you have this guy, and then you have, so C is a 3 form, which is it's a gauge field. Its field strength is denoted by the letter G. Okay, so you have a G square term, and then you have the C wedge, G wedge, G term. And then you also have, so there are some numbers sitting here and here. Let's not worry about those. And then also you have G, plus some number NP psi Q. So this is the action, and the symmetries of this are diffeomorphism symmetry of 11 dimensions. Then you have local Lorentz, SO 1,10. You have the gauge symmetry of the 3 form. And then you have local supersymmetry as well. Okay. So the problem here is that the supersymmetry algebra, if this field content is to supply a linear representation of supersymmetry algebra, so what we should expect is that, say, if you have 2 successive supersymmetry transformations and you should take their commutator acting on any field to go as translation. of the same field up to other gauge symmetries that you have in the symmetry, right? But we see that when we, so Cremmer, Julia, and Scherk, they also wrote down the supersymmetry transformations for the field content. And when you take two successive supersymmetry transformations and add them on the gravitino field, for instance, you see that this does not quite work. You also get some terms which are proportional to the equation of motion of the gravitino. Okay, so that means there is an obstruction to the closure of the supersymmetry algebra. So from the perspective of classical field theory, it's still fine. You say that the supersymmetry algebra closes on shell, but when you quantize, that's clearly a problem because you need linear representations for the algebra to close. Okay, so if you demand that the fields satisfy the equation of motion, then it's not a linear space of fields that you have. So that's the problem. And so from the perspective of component fields, you are given these ingredients, you are given the field content, the action, and then you write down the supersymmetry transformations, and then you find that equations of motion are imposed on the fields. Now, from the superspace perspective, the problem arises again, but in the form of Bianchi identities. So that's the perspective that is of more interest to us, because we are going to look at the supergeometry, and we'll see what Bianchi identities have to say about whether or not you need equations of motion. So this is the superspace that was built in the 1980s, I think in the year 1980 itself. So there were two different separate papers that did this, one by Brink and Howe, and then also I think Cremmer and Becker. They both constructed the 11-dimensional n=1 superspace. Right? So by n=1, we mean that this is a minimal supersymmetry in 11 dimensions. So it has 32 real supercharges. The idea is you have 11 bosonic coordinates in this superspace and 32 fermionic ones, and supersymmetry on that space, or on that superspace, is realized by translations in the fermionic directions, right? So they start with Gilbine one form. So it's denoted by the HET. It can have both bosonic and fermionic indices, and then they have say so in the Gilbine formalism we also need the spin connection. Omega AB, let's say, and this is valued in the Lie algebra of the local Lorentz symmetry. So SO 1, 10, right? And then we also have the 3 form. This is going to be a super 3 form, C N N P, and then its field strength is, right? Very good. So in any theory of superspace supergeometry, from the frame you define the torsion. Torsion is defined as, this is very standard textbook stuff. It is defined as the Lorentz covariant exterior derivative of the frame. So if you write it out, it is going to look like this: dEA plus omega EA or maybe the other way around. Let me switch the order. The other one also works, but up to a sign. So, and then you define the curvature to form. Definition goes as RAB is the exterior derivative of omega plus omega AC which with omega CB. Okay. Now these are defined because then immediately you can see that there is a Bianchi identity that has to be satisfied by the torsion, which goes as ETA must be equal to EB wedged with RBA. So this is the torsion Bianchi identity that is imposed by the supergeometry. Okay, and then you can also show that there is a Bianchi identity satisfied by R also, which goes as ER is equal to omega AC wedged with RCB. Okay. So in the rest of the talk, we are mostly going to ignore the curvature Bianchi, because you can prove that if the torsions are if the torsion constraints, if the torsion Bianchi identities are imposed along with some set of conventional constraints, then as a consequence, the curvature Bianchi identities are automatically satisfied. It goes by the name of Dragon's theorem. So, so all we will be interested in is the torsion Bianchi identity. But on top of this, we also have this 3 form, which is just the exterior derivative acting on C is G. That would mean that if you make another exterior derivative act on G, it should be 0 because of the fact that D squared is 0. So the third Bianchi identity that we will be looking at is that D of G must be equal to 0. Okay, so this is very traditional superspace differential geometry. So what Brink and Howe did, for instance, was to say that we are going to make an assumption that all of these superform superfields, they do not have at any theta level any spurious fields other than the degrees of freedom of 11-dimensional supergravity. Okay, so any component field of the superfields that we have for torsion and curvature and so on, they must have only the physical spectrum fields of 11D supergravity and nothing else. Yes.
Interrupt. So there's one chat message from Dan. So which remarks that he thinks that the last boxed equation should not have an omega.
This one?
I think so. Yes. He says, yeah.
This one?
I'm sorry. Then you can also unmute yourself and you can say something. I think we will hear you. Do you want to try this, Dan? Can you hear me?
Yes. Dan has unmuted, but we can't hear him.
We can't hear. Is he saying something? I'm sorry, because it was saying recording in progress, right? So your audio should work.
Yes, Dan.
Yeah, Dan is unmuted, but Dan is not saying anything. He can speak through.
Yeah, it doesn't look like that, right? Something is wrong with it.
There isn't, because this is what the Bianchi is for the curvature.
Omega is distinct connection, superspace,
Yes.
superlaurence connection, right?
Yes.
If you have the omega term, then it probably shouldn't be a covariant exterior derivative. Right? I mean,
Oh.
omega is the
Yeah. I think I think I should have written this.
something like that.
Yeah.
Then I'm sorry that we cannot hear you, but are you fine? Are you fine with this correction? Probably also here another. I'm sorry guys, I'm on my phone.
I cannot see anything on the chat.
Yeah, so he says that there should be 2 terms. But don't worry. So
Yeah.
so he says his mic is not working, so it's not our fault.
Okay.
But so yeah, I just wanted to let you know. I'm sorry.
All right. Yeah. Okay, I'll see.
Yeah, there should be a covariantization on both indices. No.
I think
We put 0 on it.
Yeah. 0.
Yeah.
Yeah. Yeah.
Yeah.
Yeah. That's right. Yes. Right. Okay. So.
He likes it. Yeah.
Yeah. All right. Right. So how do equations of motion appear? So Brink and Howe now say that there are no spurious fields in the components. So that's one assumption. And the next assumption that they make is a set of conventional constraints that they impose. Just leave these three for a moment. And they give you one is only components are fields of 11D supergravity theory that was just described in components. And then they make an assumption that these are the conventional constraints that they will impose. They are of this kind. You have any bosonic torsion and their fermionic legs along the form directions must be equal to gamma matrix. It's a constant essentially. And then this is at dimension 0. So I may tell you if you have any questions how to count dimensions of quantities, but let's say at dimension 0, this is the constant that you impose. And then at dimension half, you set these to 0. That's dimension half. And then at dimension 1, all bosonic torsions are 0. Right? And then for the 4-form field strength, you say that GABCD, right? This superfield. So the superform that we have, we can have form legs along all the 11/32 directions that we have. 11 bosonic and 32 fermionic directions, right? So if you pick out this component where all your form legs are along the bosonic direction, this is dynamical. So can be a non-zero dynamical field. And this dimension 0 component is gamma AB. Okay. So this is a constant non-zero. Other than that, all other components of G are 0. Okay. So you want to satisfy or solve these Bianchi identities subject to these 3 conditions. And when you do, you derive all the components of the torsion to have certain constraints. And then you go to other, so essentially these guys, when you write down, so this is a geometric identity that we wrote down, but you can always choose a frame basis and then decompose it in the frame components. And when you do, you look at the different components of the Bianchi identities, and then you are eventually led to the equations of motion of all dynamical fields. Okay. So for the spin 3-half gravity now, you get the Rita-Schwinger equation, and you also get the Einstein equation, and then you also get the equation of motion satisfied by the 4-form field strength. Okay, so a choice of these constraints, these conventional constraints and these conditions, along with the Bianchi forces on you the superspace to be on shell. So this is the superspace perspective. Yes.
May I ask a very stupid question as no expert on superspace? Is there any way to motivate this conventional constraint from a physical point of view?
From a physical point of view, there is one argument that you can use to organize your thought, which is the dimension counting. So your various component fields, they appear in the action, so you can give them a mass dimension.
Yeah.
And these various torsion components and the components of this form, they also have their own mass dimension. So you cannot arbitrarily put things into arbitrary components of the torsion or the curvature, right? So what can you do? You can choose the dimension 0 guys to be some constants, and then the index structure tells you that, all right, what object do I have that can fit? So you do have
to say that there would not be any physical fields which you could put there.
Right.
So, but you still have to put something. So,
Right.
and you just choose from the objects which are at your hands. You
Yes.
know. Okay.
So that's one argument that you use, and then one has to be careful that any arbitrary choice should not clash with the Bianchi identities that you have. And for instance, this one, it's not very trivial to see why this should always work with the Bianchi identity. And when you actually try to see, pick out that component of the Bianchi identity where this guy gets involved, you see that there has to be a particular gamma matrix relationship that has to be satisfied in order for this to work. And in 11 dimensions, you have a certain Fields identity, which helps you to show that that identity really works. And this is not an obstruction. This is a valid choice. So these kinds of arguments you use. But even then, for instance, we could have chosen a 0 here, let's say, things like that, right? So if you go to a textbook, for instance, Wes and Becker, where they do this entire thing for 4D n equals 1, at the end of, I think, chapter 14 or something, they derive the Bianchi identities. They provide you with a set of conventional constants, and then they make a comment that various choices may or may not work. It's a process of trial error by which we arrived at these constraints, and that's it. So there is no mathematical streamlined justification that I can give you for this.
Isn't it just filter definition, right?
So what?
I mean, if you choose one set of constraints versus another, as opposed, isn't it a matter of filter definition that relates one choice to the other choice?
But could you, for example, set all of them to 0? I mean, I
No, no.
so
I mean, the convention. I mean, your question is, how can I say this? There is a minimal set of, there are certain constraints that are needed to have a theory alive, right? You have to have non-zero degrees of freedom. But I thought your question is non-unique about non-uniqueness of how.
I mean, my question was very stupid. I was just, how do I see that these are exactly the choices I should go for? You know?
Oh, I see. Your question is not about what about other choices you could have, which also need to have that. Why do you pick one and not the other?
Yeah, I mean, I was.
That is the physical.
Okay.
That part.
So you can relate all of the allowed choices by
Yes.
Yes. Yeah, that's true.
So can I ask a question?
Yeah.
So would this conventional constraints in component format, would it be similar to the algebraic constraints on the auxiliary fields? And if there were a theory with off-shelf supersymmetry.
Right. So this is still on shell, by the way. So this already imposes the equations of motion. So it's not in the, if you take this and project it to components, you are only going to get what they have in the original 11D paper. And that paper doesn't have any auxiliary fields at all. Okay. So you cannot map these constraints to any existence of auxiliary fields.
Yeah.
Right? Any other questions? No. Okay. Right. So now the question is, how do we fix it? Can we fix this? Can we choose maybe a different set of constraints, and then we are led to we are not led by the Bianchi identities to equations of motion of dynamical fields, right? That's the question that we're trying to solve. And through a series of papers over more than 5 years, a 4D n equals 1 symmetry, the Becker group has succeeded in throwing 4D n equals 1 supersymmetry off shell. And that construction is the bottom-up approach, and parts of it I have written down here. So I'll now explain that to you very quickly before we go into the supergeometry stuff. Okay. All right. So solution, partial. So by partial solution, I mean we are throwing partial supersymmetry off shell, but the rest is still on shell. So the bottom-up approach is Let me give you a couple of references from where you can look up the details. So essentially what we are trying to do is to throw partial supersymmetry off shell. So what we are going to do is to make a trade-off. To gain it, we are going to give up the entire nonlinear field theory and we are going to linearize it. So linearize around a flat background. And the flat background is of this type. You have, this is the background. 4D equals 1 superspace cross a 7-dimensional internal space. This one is a 7D Riemannian manifold with a G2 structure. Okay, so why is this? So we have, from the 4D perspective, there is n equals 8 supersymmetry, right? 32, 4 times 8 is 32. So of this, so if you wanted to take the multiplet of 11-dimensional supergravity and write it in a 4D n equals 1 superspace formalism, then clearly you are picking out one particular supersymmetry out of these possible 8, right? So how do you do it? The idea is you choose a background which picks out a particular subset of 4 dimensions for you. Okay, so that the way it is done is that Y being endowed with a G2 structure, it means the following. You have a spinner. So essentially you have, so there's a lot of detail, mathematical detail going into what it means for a manifold to have a G2 structure. But the thing that will be important for us is this fact. So you have a 7D, so 11D spinners can be decomposed in terms of 4D spinners tensored with 7D spinners. Okay. So why is this unique to spinners? It's because the number of independent spinners that you can have in any arbitrary dimension goes as exponential of 2, right? So in 11 dimensions, you have 2 to the 11, 2 minus 1 independent spinners, right? So in 4 dimensions, you have 2 to the 4 over 2 minus 1, and in 7D, you have 2 to the 7 over 2 minus 1. Okay, so now if you take a simple product of these two, that matches this number, right? But for, say, for instance, if you had a vector in 11 dimension, it usually doesn't go as a 4D vector times a 7D vector, but 11D spinners, they have that. So it's because of the exponentiation of the dimension. Now, this would not work if you had an even dimensional spinner, and if you are breaking it in an odd plus odd split, then you would be falling short by a factor of 2. Okay, but because we have an odd dimension and we are splitting it into an even plus an odd, therefore this product exactly matches that. Okay, now what does that mean? This means that you can imagine. Yes.
What do you mean by independent spinners?
Independent components of a spinner. The spinner space in 11 dimensions is this dimensional, right? It's a vector space. So it's a 32 component spinner that you can have. If a spinner has 32 components, then the vector space that is spanned by it is 32 dimensional.
What you've written there looks like it's only 16 rather than 2. Do you mean these minus ones?
Yeah.
No, you don't mean minus 1. Just 11 over 2. It's just 32.
Oh, yeah.
And it doesn't match if he just goes into minus 1.
Yes, you're right. The minus ones. Yeah, exactly. Yeah, I was going to the while spinners, but these are the deluxe spinners.
Yeah, it's a little bit tricky, right? Because they can be complex or they can be
Yeah. So what I was writing down was maybe complex or maybe while if you cut it in half, right? Right. So so what was the question again?
Yeah, I was actually pointing at
Okay.
about the
Okay. All right. So now what we are going to say is that So essentially, how does it go? It goes as, if you have an 11-dimensional spinner, it can be written as, so a basis that you can choose for 11-dimensional spinners can be all in this form, in this tensor form. So we are going to have something like this, psi alpha hat, if you write it as product indices. Okay, so this psi alpha I can be written as eta alpha, eta I psi alpha plus I and then so what are these underlying indices? These are the coordinates on the internal space. Okay, and what we have written down here is a basis, essentially. So the basis of 11D spinners that we are choosing, they have this form. Eta is the 7D spinner, and then we have a psi, which is a 4D. Okay, and then you have gamma A eta, another 7D spinners, and then you have 4D spinners like this. Okay, so if you take these as your basis, you can span the space of 11D spinners in terms of them, and this is how it is written down. The decomposition of the spinner indices happens this way. Okay.
Can you say what is the eta?
Eta is an arbitrary spinner of SO7 of this Y internal space that we have. Right now, at this point, this eta can be any arbitrary 7-dimensional spinner that you can choose. Okay, this is a choice of basis that you're making. But the fact that this internal space is endowed with a G2 structure lets you choose a specific eta, which is associated with the G2 structure in the following way. So let me write here. The 3 form, which is associated with the G2 structure is, or essentially this is called the G2 3 form, or the G2 structure, is this guy. Okay, so the internal space having a G2 structure means that there is a covariantly constant spinner in that internal manifold. So if you choose that eta in your basis, then you are essentially picking out a particular basis, and then that tells you which 4D equals 1 supersymmetry is the preferred one, which you are going to keep manifest in your formalism. Okay, so this is what goes into the construction, and then what you say is that you want to take all the component fields of 11D supergravity, and you want to embed them in superfields of this 4D equals 1 superspace. Okay, and when you want to do that, you would like to go to the prepotentials, which are unconstrained. By unconstrained, we mean that they can have reality conditions or chirality conditions, but they won't have any constraints on them, which will imply a derivative sort of a constraint on the components, or a dynamical constraint on the components, right? So that entire program was done in here, and a brief summary of this is on this side of the board. So these are the prepotential fields. Okay, so this is a real superfield, a spinner, just an arbitrary spinner, no chirality constraint on this. You have a real vector field, a real scalar field, chiral, real, chiral, and so on. And these are the different, so to speak, component fields that are embedded at the various theta levels, right? And I have color coded them to show you that things which are just in the components which are just in white, they are in the physical spectrum. The ones which are this color, these are the auxiliary fields, and the ones which are this one looks a bit like yellowish green. These are compensating fields in the spectrum, so they do not appear in the spectrum, right? So the compensating fields are required because you are making a 4+7 decomposition. There can be an appearance of a conformal symmetry, which the 11D theory doesn't know anything about. Okay, so those superfluous symmetries have to be compensated for, and the compensator fields they do just that. Okay, it's kind of like how 4D equals supergravity is equivalent to the superconformal gravity coupled to a conformal compensator. It's the exact same story that happens here as well. I mean, not exact, but in principle similar story. Okay, so I did not write down the other ones. And if you do a counting of how many degrees of freedom we are encoding in these superfields, you see that it's the total counting is this. So if you count the real dimensions of degrees of freedom, or the real degrees of freedom, if you do that, you see that there are 376 bosonic ones and 376 fermionic ones. So on top of the one, there was a mismatch by how much again? Let me remember the numbers. Off shell, we had 175 bosonic and 320 fermionic in the original multiplet of 11D supergravity. So essentially what we have done here is we have added 201, 201 bosonic ones and 56 fermionic degrees of freedom. These many auxiliary fields have been added to the spectrum. And you do not count the compensators because, like I said, they do not appear in the spectrum. They suffer Stuckelberg-led shifts. All right, so that's the bottom-up approach. Now, the question is what's going on at the level of supergeometry, right? What are the, so you can construct this, right? And then you can, and in the later paper here, what was worked out is an expression. So these are pre-potentials which are housing all the component fields, but you can always ask, can I construct a superfield which at its leading order in theta, which is the theta independent part in the expansion in theta, will have the frame or the gravitino or the spin connection and so on, right? So that was worked out in this paper where we constructed superfields out of the pre-potentials, which at their leading order had the frame, the gravitino, the three form, and so on. And once you have the component fields like that, the language that we are using is that, for instance, if you have a superfield which looks like this, okay, it's a superfield, so you can do a theta expansion. Then you have at theta equals 0, you have say EMA and then other orders in theta, right? So because this guy at its theta independent level has this, we usually denote them by the same symbol. So this can be a superfield. This can also be thought of as a component field, so to speak. So, but really they are superfields. And then if you want to find what their supersymmetry transformations are, because you are using 4D n equals 1 superspace, it is explicitly manifestly supersymmetric, you can simply act on these guys with the fermionic derivatives to generate super translations, and that would be the supersymmetry relation. Okay, so by using the 4D n equals 1 supersymmetry algebra, the modified supersymmetry transformations were derived. Okay,
but this is just then an n equals 1 supersymmetry algebra.
Yes.
Right? I mean, it's not with all the 32 supercharges, but with just a subset of them.
Yeah, the part which is made off shell by introduction of these auxiliary fields, that was calculated. Okay, so the other non-manifest supersymmetries are non-linearly realized, and they would require equations of motion. All right, so this is the bottom-up approach. Now we are going to, we have 15 minutes left, and I'm going to show you what the top-down approach is, in which you actually derive torsion constraints, which then can be solved in terms of pre-potential superfields which are not constrained. So this would be the answer to a question which is geometric. So we had the answer first, we did not have the questions or what constraints imply that this would be this pre-potential superspace embedding of all your fields. Okay, so for the last 15 minutes that we have, let me describe that. And that is the project which is right now ongoing. And we have finished deriving torsion constraints all the way up to dimension 3/2. So 2 and 5/2 are the only dimensions that are left. And it is believed that higher dimensional torsion constraints don't need to be solved because they only impose some derivative identities between curvatures and torsions and so on. Okay, so we are pretty close to finishing that part of the project as well. So let me describe how it is done. So what is this n=1/8 superspace? And so this is the top-down approach. 11 the n=1/8 superspace. So like I said, we have the full 11/32 superspace whose coordinates are say hatted indices. It has say xm hat, which can have 11 bosonic indices, and say theta alpha hat. And so in alpha hat, let me say that it has 32 components. Okay, so let me not distinguish between alpha hat and alpha dot hat. So we are restricting this to xm theta mu theta bar mu dot. So these are the indices of 4D n=1. And we have some internal coordinates to parameterize the internal y manifold. Okay, so there is 7 of these. So essentially what we have is 4/4 plus a 7. So this is the superspace that we are truncating to, right? So so what we are doing essentially is that in this say entire 11D space-time, we are picking out a subspace where 28 of the 32 fermionic coordinates are set to 0. Okay, but yeah, sorry, was there a question? No. So what we are doing essentially is we are saying that theta m alpha is 0 and d theta m alpha is also 0. Okay, so what does this mean? Remember that any arbitrary 11D alpha was decomposed this way, right? Gamma a theta I, theta a alpha, and similarly for the alpha dot, right? So these would be those. So you can imagine that this is just n. Okay, so those are these 7 extra theta m alphas and theta bar m alpha dots as well. We are setting them to 0, and we are setting these forms to also these one forms to 0 also, because we don't want to go off the constraint surface. Okay, so this is the superspace that we are trying to construct. All right. So the background around which we are doing this, the 11/32 flat superspace, okay, is the full guy, and then we are constraining ourselves to this 4/4 plus 7 subspace of it. So that background being flat means you can choose a global Wilbine. Okay, so a global Wilbine of this form can be chosen. That is a standard flat superspace relationships. Gamma A, alpha beta, d theta beta, and for E0 alpha, you only choose d theta alpha. So for instance, if you look into Wessenberger, they have exactly this, but instead of having hats, they don't have any hats, they are doing 4D. But it's the same thing. And this being global means this choice of frame can be done globally up to rigid SO 1,10. Okay. So there is no local Lorentz business. It's not gauged. It's a rigid global SO 1,10, after which this can be chosen. right? And then the background value for the G field has to be also given, right? So this is the background value for the frame from which you can derive what the background values of the torsion, etc. are, right? One thing that I should mention is that because you have rigid SO1, 10, that means the spin connection for the background is also 0. Omega 0 is 0. And that's also very simple to understand because spin connection is only needed because you are trying to gauge the Lorentz symmetry. Because you don't have the gauge Lorentz, therefore you can choose spin connection to 0. Now, what is the background value of G? Okay, so the G0 that we are choosing, again, it doesn't have any component which is which is non-zero except for this G0 A B gamma delta. We choose that to be again this guy, and all other components of G background G is 0. Okay, so again you have to make sure that this choice of the frame and the background value for the 4 form does not clash with the Bianchi identities that you have derived, because the background has to be a solution, right? It cannot be an arbitrary background. And then you go on and check that they do satisfy all the Bianchi identities. And like I mentioned, there is an 11-dimensional Fields identity which comes to help you to show that this choice is valid. Okay.
So is this flat superspace a choice, a solution that you are taking and expanding around?
Yes.
One of the solutions.
Yes. Yes. Like I said, so we are making a trade-off. We are linearizing the theory. By doing that, we are gaining a partial off-shellness of a supersymmetry. Okay. So the background around which we are going to fluctuate is this one.
Can you do the curve one, like ideas?
Good question. I'm not sure. I haven't tried it, but we can try. We can see what that means. Right. All right. So very good. Now, what are the what are the fluctuation fields? There needs to be some. Say, let me give you a quick description of the notations that we use. So you have the full torsion, right? So you are going to write it as, in tangent space frame, we are going to write it as E wedge E times T, 2 indices, 2 form indices, and A, right? So that basis E is going to have background value and a linear fluctuation. So A, B, C, say CV, let's say. So B, and then B0 plus H, C, TCBA, that is what it should be. I'm string off. So let me write it here. Now that T we are writing as plus the linear fluctuation in tangent space of the torsion component. Okay, so you can take this equation as the definition of the linear fluctuation of the tangent of the torsion component in the tangent space. Okay, so you do similarly with the 4 form. You say that G is going to be 1 over 4 factorial. Then you have E plus E0 plus H CB. So ECBA, and then G0 ECBA ABCD plus the fluctuation. Okay, so these are the definitions of the linear fluctuation fields. Okay, now you take these fellows and you plug them into the Bianchi identities that you derived. Okay, up to linear order. That's what you're doing. Is this definition clear? Are there any questions about this? No? Okay, clear. So now you plug them into the Bianchi identities and you derive the linearized Bianchi identities around the background that we have chosen.
May I ask one question?
Yes.
So these new quantities which you have introduced, so they depend on eta, right? So on the spinor eta, which is given by a G2 structure.
What do you mean they depend on eta?
So I mean to really compute them explicitly, you have to know eta, and when you use the Bianchi identity,
right,
you also use the differential identities for eta, which is given by the G2 structure.
Yes. So essentially, what we do is say, so if you are choosing, say, one of these guys to be a spinorial component, then you would like to say, how can I extract the decomposed parts? For instance, so if you have any guy having an alpha coordinate, so let's just look at the alpha I part, the top half. So it would be eta I psi alpha plus I gamma A eta ith component times psi A alpha, right? So how do I extract these guys and make it independent of the eta, right? So what you can do is say that the eta spinors that we have, you can choose to normalize them. Okay, and you can also prove from the symmetry properties of 7D gamma matrices that eta and gamma A eta are orthonormal. So if you take something like this, you get a 0. If you take gamma A eta transpose, gamma B eta, you would get delta A. Okay, so you take this and then therefore when you do this, you would just simply be projecting onto this component.
So similar to the pure spinor constraint when you have an SU3 structure?
Pure spinor constraint. I'm not quite sure.
Don't worry. I mean,
Right.
I'm also not sure whether I remember completely. So for
Right.
SU3, there is something similar. You know, you can normalize them, but so this is not enough. So there's also some additional constraints. So I think you can express them as a pure spinor or in terms of a pure spinor constraint.
Okay.
And I think it's something similar.
Something similar. Okay.
Yeah.
All right.
So when you put in so when you write the gamma matrices there, so is it all of the gamma matrices or is it just
these are the internal ones? So essentially what we do is you have an 11-dimensional gamma, right? You choose a particular representation for it where you have a gamma 11 is equal to a 4-dimensional gamma tensored with a 7-dimensional gamma. So so that would be these guys. And for this, we do not choose a specific representation. We just use the representation independent properties of 7-dimensional gamma matrices, and that is sufficient to give you these results. So for instance, you want your 11-dimensional spinor to be anti-commuting. Your 4D part is already anti-commuting, so the 7D part can be commuting, right? So from the fact that this is commuting, but this guy has a symmetry property, you can show that this is 0. This has to be 0. Similarly, you can show from the Dirac algebra satisfied by the gamma matrices and the property of gamma AB, whether it is symmetric or anti-symmetric with respect to transposing, you can show that this has to be delta AB and so on. So these results are representation independent, but we are essentially choosing a set of gamma matrices which is adapted to the spinor decomposition that we are trying to do. Yeah. Oh, I think I probably ran out of time, but I can give you just a few basic ideas how to proceed from here onwards. So you put the linearized fields in the Bianchis to get linearized Bianchi identities. Right? So you get some for the torsion, you get some for the curvature, you get some for the 4-form, but the curvature Bianchis we are not too much worried about. We take the torsion Bianchis, the linearized ones, and then we try to see what sort of constraints are imposed on the linearized fluctuations of the fields, for instance, this one and that one and so on. So there is some representation theory that goes into that. For instance, if you have a component that looks like, say, this, right, it's a dimension 3/2 component, you would like to SL2C irrep decompose this guy. So change these guys into a bispinor index, and then you have another one here. So you then would like to see what irreducible components this guy has, and then those things will now be put into the Bianchi identities, and then you are trying to see what derivative constraints the torsions would satisfy. Okay, And the final idea is once you have a full set of torsion constraints, you then propose some solutions, unique solutions in terms of pre-potentials which are unconstrained. And then you map it to the previous story that I told you. Okay. And then final motivation is the reason why this is important. Once you know what the supergeometry is like, you can have, you now have access to the Riemann curvature, the linearized fluctuations of the Riemann curvature. So you can construct terms like R squared, R to the 4. So you can now write down higher order corrections to this theory. Now, eventually that may or may not lead to a low energy effective action of M theory and so on. So that would be the end goal, to push this forward all the way and see what you get. Right. So thank you. Yes.
Sorry.
Please go ahead.
Could I ask, so you're very much basing this on a 4+7.
Yes.
Could you do it some other way? I mean, a 5+6 or something like 6+5 or 7+4?
In principle, this could be tried, but
wouldn't you get more structure in it? I mean, I can't remember quite how it goes with superspace, but isn't your basic reason for this kind of thing that you can't do a proper superspace in 11?
yes.
But you don't need to go down as low as 4 in order to be able to do it. You get more structure.
It's possible, but I think one motivation for trying 4+7 was compactification to 4 dimensions. If you can, for instance, it's known that from 11D to 4D, if you compactify on a internal manifold with G2 holonomy, then you have 4D n equals 1 surviving, right? So that could be a possible motivation for why you're trying 4+7.
Physics.
Yeah.
Phenomenal.
Yes.
Any further questions?
Yeah. So towards the end, when you were describing the motivation, you said you can compute higher derivative corrections. So, but I mean, how do you know how high do you have to go?
Yeah, that's a good question. So essentially, the conjecture that was being made that if you have just R squared plus R to the 4 and then this off-shell partial supersymmetry, then you might get M theory low energy effective action. It's actually based on an analogy that we have in electrodynamics. So in supersymmetric Born-Feld, it was proved by Becker and Galprin. So let me not write down their names. They proved that if you have Maxwell and then F to the 4, and they also added in a mix n equals 2 nonlinear realized supersymmetry. That uniquely leads to supersymmetric Born-Feld. This was proved, like I think back in the day, a few decades ago. So, what is this guy? This guy is the low energy effective action of open string field theory. So that kind of analogy is used to conjecture that this may be the way to go for gravity. Okay. So just this and that is enough to give you a Born-Feld, which is actually non-linear. I mean, it's up to all orders. Okay, so it has the square root of determinant form.
So in your case, how far have you computed?
So right, we actually have not immediately after giving the prepotential formalism, there were two ways that we could choose from. One was to actually find out the entire supergeometry and settle that question. The other one was to just take whatever construction we had and then use that to compute the curvature to form the torsion and so on from the prepotentials, and then immediately start computing that. So both of those options were explored, but none of them has been completed yet. So in the supergeometry aspect, we have up to dimension 3 half constraints fully derived. Okay, and in the other approach, I think William started it, and he has made some progress, but it's not completely finished either.
Oh, so these derivative corrections, they are related to the
yeah, you have to have, so if you want to do R to the 4, you want to know all components and all the constraints that are imposed on the curvature, all the curvature constraints and so on. And then you can wedge them together and then you find higher derivatives.
Okay, and that will take you beyond 3 half?
Oh, you mean dimension 3 half?
In terms of constraints? I guess my question is that how is this the derivative corrections are related to the dimension of the constraint? I mean, is there
No. What I'm saying is that we are trying to finish the finding out everything that you can about the supergeometry, and then we'll start calculating the higher order ones. Yes. And but what you are saying has already been started. Like William at least started doing some of that stuff, but I did not specifically look into it. So maybe after I finish this, that would be the next thing to do that. Ideally, yes.
Okay,
Any
great.
questions?
So, do we have any question from the Zoom audience? I cannot see anything, but when there is anything, you should tell us. Okay, seems to be not the case. Then let's thank our speaker again for a very, very nice seminar. Thank you very much. And I will stop the recording. I will at least try.